tab? Yeah. Oh, okay. So hopefully everyone could hear what I said up to this point kind of okay at least. Okay, so we have add 2, we have infer. Add 2, we're saying the output is exactly 2 more than the input. Infer, we're saying the output is greater than the input. This is not going to work for our verifier because we have what's known as a modular verifier, which means we're verifying the functions modularly. And the verifier is only looking at the specifications of functions that are called. It's not looking at the definitions. So what that means is here, when we're trying to verify add 2, we don't actually see this whole picture. We see this part of the picture. We see that infer's output is greater than its input. We don't know anything else about it. So it could be that infer adds 1,000,000. That satisfies the specification of infer, violates the specification of add 2. Right, so that's kind of the potential problem you can run into with modular verifiers. You can have specifications that all look correct and then in fact are all correct, but then you can't verify them and it can be tricky to figure out why. In some earlier work before this paper, also with Ranjit and Ruzica and also Anton Su and Maxwell Bland, we came up with this scheme to try to help people diagnose these errors that you get from a modular verifier. And the idea was these error messages you get from the verifier are kind of hard to understand, so let's give counterexamples instead. Ideally, we give what's called a concrete counterexample, which is an actual input and output that violates the specification, right? If your specification is actually wrong, that's possible to do. In a case like with add 2 and infer, the specification is not actually wrong, right? It's just not being proven. And so we came up with this notion we call an abstract counterexample to illustrate this kind of mistake. So to kind of show what an abstract counterexample is by example, here's an abstract counterexample for this add 2 case. It says that add 2 of 0 is equal to 3, violating add 2 specification if infer of 0 is equal to 2. So the key word here is if, right? Infer of 0 does not equal 2, but infer of 0 equals 2 is consistent with the specification on infer. Oops, sorry, I haven't updated specification there, but infer 0 is equal to 2 is equal to the kind of specification of infer where the output is greater than the input. And it violates the specification of add 2 if infer of 0 equals 2. So the way to fix this is to make the specification on infer stronger to rule out this kind of bad possibility of input and output, which is done by saying that the output is exactly the input plus 1. Now this add 2 infer case is kind of boring and simple and can be easily solved by inlining or something also, right? But I want to point out that this gets more complicated and more interesting with more complex functions, right? And you end up in cases where you need like inductive proofs that can't just be done by inlining. So here I have a function concat. Concat has a specification that says the size of the input is equal to the sum size of the output. That sum size function is basically taking a list of lists and summing up the sizes of all the lists contained in the lists. So concat is taking a bunch of lists and sticking them all together. It relies on this helper function app that also needs a specification for verification to succeed. And the specification I have here is insufficient, so we could get a abstract counterexample there as well. I'm going to gloss over the details of this for now. The details of this abstract counterexample are not that important. So that's kind of the previous work, finding these concrete and abstract counterexamples. What we then said is, well, we're getting these counterexamples, can show them to the user. Hopefully they're helpful to the user in debugging. But really, it would be nice if we could just automate the process of modular verification and automate finding these specifications. So the natural way to do this, if you have counterexamples, is throw this stuff into a counterexample-guided inductive synthesis loop, or a SIGPLAN loop. So that's what we're doing now. So we now have the code and the specifications written by the user, which is what we're going to try to prove. And then guided by abstract counterexamples, we're going to try to synthesize new specifications to support those user-driven specifications. As we synthesize specifications, we might also find concrete counterexamples to the synthesized specifications. Those can be given to the synthesizer to help guide it. We might find concrete counterexamples to the user specification. If we find a concrete counterexample to the user specification, we just return that to the user because there's no kind of ground truth to say, is the bug in the user's program or is the bug in the user specification, right? That's something they have to kind of decide and fix. This is the concat app program from before, but without a specification on app at all. So I'm just going to kind of point out app is called in the last line of concat there, right? And basically what app is doing is it's appending two lists together. And if you try to verify this, you're going to get a verification error because we need to know something about what app does. And we can explain the verification error you get with an abstract counterexample. If appending two empty lists gives you a list with 0 in it, then concat of a list with two empty lists in it gives you a list with 0 in it, which violates the specification of concat. So now we know that whatever specification we have for app, it has to say that two empty lists does not yield a list with 0 in it. We can also actually just run app for real on two empty lists and say, well, app takes two empty lists and gives you an empty list, so the specification has to satisfy that, right? And so now we have two goals for a synthesizer. The thing that's indicated by the abstract counterexample has to be false. The real evaluation has to be true. And so we can synthesize a specification. Maybe the size of app's output is always 0, right? That is false when your output is a list with 0 in it. It's true when when your output is an empty list. Well, of course, it's not a correct specification for app, right? And so then we get a concrete counterexample to our synthesized specification. And so we add that as a new synthesis goal. We now know that a list with 0 in it and an empty list gives us a list with 0 in it. And so then we can say, well, maybe the size of the output is the size of the first input. And then, of course, this is not sufficient because you might have elements in the second input. And so we get another counterexample. And we keep on doing this until we have enough counterexamples to guide us to a correct specification for app, meaning a specification that both is true about app, correctly describes app, and is sufficient to verify the specification on concat. We can prove some theorems about this. Soundness is somewhat trivial looking at the algorithm because we're calling the verifier over. Oh, I should say, by the way, these are informally stated on the slide, and look at the paper for details. Soundness follows pretty easily from the algorithm if you assume soundness of the verifier. Because basically what we're doing is looking for a set of specifications that let the verifier successfully verify the code. We run the verifier. If it verifies the code, we finish. Otherwise, we continue in the loop, right? So soundness is pretty straightforward. We can also prove some completeness properties relative to the verifier's ability to reason. So really, what we can say, and we actually state a more general version of this in the paper, but if there exists an assignment of specifications drawn from this grammar that would let the verifier succeed in verifying the code, we will find that assignment of specifications. The version in the paper is actually more general than this. It describes requirements for a synthesizer for a particular language that would let you state something like this. We implemented it in particular for a synthesizer that synthesizes Leah specifications. I'm going to kind of gloss over the details of that a little bit for time. But the basic idea is we're taking these Leah specifications and we're using an SMT solver to synthesize definitions. And so we have a bunch of templates that look like this, basically big if then else's, just select do you want an equality, or do you want a less than, or do you want a greater than. This doesn't get you conjunction or disjunction, but as the synthesizer runs and fails to find a specification, we create the possibility for conjunctions and disjunctions of these in our template. There's some kind of tricky corner cases where you can run into things like the set of specifications you have has made other specifications you need unrealizable, or there's like no specification that you can synthesize given these other specifications. And so that requires backtracking, which requires using things like unsat cores to figure out where problems are. So using an SMT solver here lets us do some of that. We experimented with using SIGA solvers and such, but it wasn't quite enough to like get us where we needed to be. Yeah. So there's much more details about how all this works in the paper, and how exactly this corresponds to refinement types and how we get refinement types into the synthesizer and vice versa. We evaluated this on a mixture of benchmarks from prior work on liquid Haskell, some benchmarks from our prior work on concrete and abstract counterexamples, and a couple other case studies that I'll talk about. Most of the time when we're successful is spent on symbolic execution. Interestingly, when we time out, a lot of the time is spent on synthesis. So synthesis is usually pretty fast, except when it's not, and then it really slows us down a lot. We have a couple so these are all pretty small benchmarks, all terminate in under a minute. We have a couple larger case studies in the paper. I'm going to highlight one of them, which is an implementation of k-means, which has this one k-means one function that has a specification on it, and involves 34 other functions that we have to synthesize specifications for, including merge cluster nearest and centroid called in this function are functions with quite tricky preconditions. And so what happens with this is kind of interesting is we spend about a fourth of the time just symbolically executing k-means one, trying to find concrete and abstract counterexamples to illustrate what's happening with these functions here. And then everything else happens pretty easily with the other 31 functions or whatever it is. There's quite a bit more in the paper. Like I mentioned, we have formal statements of and generalizations of the theorems. We have much more on the Leah synthesizer and how that works. We have a little bit about synthesizers for other types, such as sets. And we have a bunch more benchmarks, including comparisons to some other similar tools, and evaluations on data structures from Okasaki's functional programming textbook. Thanks. I'm happy to take your questions.
All right, so we'll take a few questions. And if you don't mind, speak into the mic and please introduce yourself.
I am Ravi Mangal. In practice, you would expect users to review the synthesized specifications.
Sure. I mean, they can if they want. The code is verified based on the specifications, right? So I guess it's a question of how much you trust your modular verifier also, right?
If there's a mistake in the code and I synthesize a specification and that allows me to prove the overall theorem, then something has gone wrong, right?
So, yeah. So assuming the modular verifier is correct, if we say here's a set of specifications, let this verification succeed, then whatever your specification is that you wrote down is correct about the function you wrote down, right? Of course, it's always possible your specification is a bit wrong or your code is a bit wrong. So you should, maybe still examine things a bit yourself. But there's no possibility of or at least there's no way I can think of for our synthesizer to trick the modular verifier into verifying something that isn't true. Again, assuming the modular verifier is correct, right?
Thank you.
Yeah.
Did you try to, sorry, this is Madhu from UIUC. Did you try to look at the related problem of just synthesizing the strongest postcondition for modules independent of the client in your language, in some logic that, restricted logic that you can handle?
We didn't look at that specifically. There is work on that topic. I think you've done some work on that topic, right? Yeah, I mean, I think that there's, for this setting in particular, there's potentially an advantage to just saying, here's a specification that's sufficient to, because like typically we have some property we care about, right? And there's an advantage to just being able to say, let's find a specification for merge cluster that works, even if it's not the strongest. Because, if you make merge clusters post-condition stronger, then everything downstream from merge cluster also maybe needs something that's stronger, right? So it just slows down the process. The other thing that could be a bit of an issue is we're finding both preconditions and postconditions. So here, actually, most of the time with centroid and nearest and merge clusters spent finding preconditions based on the preconditions for k means 1. So you can always make your preconditions stronger and your postconditions weaker, or vice versa, right? So yeah, so I mean, and there's cases where you can't just rely on having the strongest postcondition here. You also need some preconditions. So I think for modular verification, it's not quite the right approach, at least all the time.
Okay, sorry, let's try to keep on track. So please take your other questions to the speaker after the session.